In this class, we'll see the optimization. Like now, where do we use? Basically, it's used in data approximation and analysis. We know data comes from a real world measurements, and now we need to understand how to use them in simulation or rendering, and how to study the general behavior, understanding the pattern, right? Where it is maximum, where it is minimum, and if there is some noise, how to remove the noise in that. That is the basic agenda of this chapter and approximation. Right? So, what is the general goal? Find the best approximation to the measurements, real world measurements. No, so in other way, mathematically, given a numerical model, uh, using a reduced set of parameters, we need to fit a best curve to the data, right? One good example is a linear regression. Suppose the data comes from a real world like this, then what is the best approximation, best model I can fit to the data, right? If it's a linear regression, then what is y equal to x plus b is the line I can fit to the data. Then what is the best line I can fit to the data, right? So the definition of best mean maximize the quality, right? So mean be as close as possible to the goal. Then we need a metric, right? Like a distance or norm that has to be minimized. So optimization is classified into many classes like a constrained, unconstrained, smooth, non-smooth, convex, non-convex. Okay, let us, our discussion is confined to constrained versus unconstrained optimization. So basically we focus on one, constrained versus unconstrained. So now we are interested in unconstrained versus constrained optimization. Unconstrained means we have to minimize the objective function f of x. I need to figure out those x where it is maximum or where it's a minimum rather, versus same minimum. We have to minimize the objective function, but here subject to some constraints on that. So in unconstrained optimization, every point X is feasible, viable for to eligible candidate for a minimum. So singular focus is on finding how the low value of f of x. Whereas in constrained optimization, where constraints truly need to hold exactly, it may be difficult to find an initial feasible point. So this typically leads to different cases, classes of algorithms, right? So unconstrained optimization problems, we consider the problem of minimizing an objective function that depends on real variables with no restrictions on their values. Then the constrained optimization problem is minimize f of x. That's all. So in an unconstrained problem, minima are only found at certain points called as stationary points. In a constrained problem, minima can be found at non-stationary points also. When you introduce a Lagrangian, the new problem of unconstrained, in the sense that the minima of the original function are found to be are found at the stationary points of the new one called a Lagrangians. So we'll see both the things, unconstrained and constrained. Unconstrained, we'll see we use a Hessian matrix and all those stuff, and constrained we go by a Lagrangian optimization, right? So now let's take the case of a single variable, say y equal to f of x. We need to find its maximum and minimum. Through calculus, we know that the first step we do is we'll find where the tangent is parallel. We find where f dash x equal to 0. Each such point, each such x where f dash x equal to 0 is called a critical point. Say I call one critical point I. Now, for each critical point, say x equal to a, we'll find the second derivative and we'll concentrate on the sign of that second derivative. If f double dash a is greater than 0, then the value of f of x at x equal to a is said to be local minimum of that function. If f double dash a is less than 0, then that a is said to be local maximum. If f double dash a equal to 0, the test is inconclusive, meaning we need to have further investigation. There are other ways, right? Also, we need to check points where f of x is defined, but the derivatives are not, as well as boundary points. Then we'll generalize the discussion to function of more than one variables, say 2 variables, 3 variables, and n variables. So let's see how to optimize. Once you understand the basic logic here, the same is generalized for a more number of variables. Now look, let's take 2 variables. Consider z equal to f of x, y. Then we know it's a surface. Now you observe this surface. Consider a point, say xy equal to ab. Then that point is said to be local maximum if f of xy is less than or equal to f of ab for all xy, however small region you take around that ab. When is that said to be global maximum? Right? Absolute maximum. When f of xy is less than or equal to f of ab for all xy in that domain. Right? So when f of xy equal to f of ab, then local minima and global minima are similar. Right? We are more interested in local maxima and local minima. Here, if you observe this surface, z equal to f of xy, point A, C, E, they're all local maxima. Point E among these local maxima, point E is the global maximum. D and G, they are local minimum, and G is the global minimum, right? And if you take a particular cross section, right, then B is said to be in this red cross section, and then B is a maximum. Whereas if you take a purple cross section here, then B is said to be minimum. But we know it is neither maxima nor minimum. No, such a points, they are called saddle points, right? Okay, so the algorithm we use is, we'll take a tangent plane similar to a tangent line, right? And we'll find the gradient there, del f. Where del f equal to 0, such points are said to be critical points. Then we investigate whether that point is a maxima or minima. That is our game plan, right? So critical points are those points, those are the candidates eligible for maxima or a minima. Now, same thing, if it's a function of more than 2 variables, here we discussed about 2 variables, if it is a function of more than 2 variables, then same logic is obtained. Get the, calculate the gradient, equate the gradient to 0, del f to 0, then figure out the points where del f equal to 0, those points are said to be critical points. Now we need to understand, using a second derivative sort of thing, we need to understand whether that point is a maximum or a minimum, right? So what we do is we calculate the Hessian, right? Compute all the points where where the gradient is 0, and compute the discriminant if it is a function of 2 variables, and the same can be extended to a function of several variables. Calculate the Hessian, that's the determinant. Dou square f by, it's a determinant of second order derivatives. No, dou square f by dou x square, and dou square f by dou y dou x, and dou square f by dou x dou y, dou square f by dou y square. Right? Then calculate the determinant. Determinant is this minus this at that point. If the determinant is greater than 0 and mainly if it's a positive definite, that is d is greater than 0, f of x is greater than 0, second derivative is greater than 0, then z equal to f of a b is a local minimum. If d is greater than 0 and f of fxx is less than 0, then z equal to f of a b is said to be local maximum. If d is less than 0, then it becomes a saddle point. D equal to 0, then it is inconclusive, right? So AB can be minima, maxima, saddle point, or none of these. All are possible here. So what is algorithm? Model that function. It may be a function of two variables or function of more than two variables. Get the critical points, equate the gradient to 0, get the critical points, and at each critical point get the Hessian, right? And see whether it's positive definite or a negative definite or a indefinite, whole lot of things, inquire, then draw the conclusion whether it's a local maximum, local minimum, saddle point, or none of this, right? So if it's a function of two variables, then this is the Hessian, right? If the d is greater than 0 and dou square f by dou x square is greater than 0, then z equal to f of ab is said to be local minimum. If d is greater than 0 and fxx is second derivative is less than 0, then z equal to f of ab is said to be local maximum. If the determinant is less than 0, right, then f is said to be a saddle point. If the determinant equal to 0, then no conclusion. Right, we need a further investigation. We cannot conclude the nature of that critical point, right? Okay, stop here, and we'll do a couple of problems in the next video, right? So understand the algorithm, and we'll do problems in the next video.